Alright, so here are some of the answers to your force diagrams assignment. So the first thing we're going to do is we're going to draw a dashed line around the object we're interested in. We'll say up is positive. Let's go over here. We're going to have a dot in the center. Force of gravity on the bird by the earth. And we're going to have an equal force upward. This will be the force of normal on the bird by the perch. So the net force in the x will be nothing. And the y, we're going to have the force of normal in the positive direction, and we're going to subtract the force of gravity. And these two forces, in fact, are going to be equal because, again, the acceleration is equal to 0. Okay. For the ice skater, the hockey player, again, up is positive, and we'll make to the right positive because that's the way we kind of been doing things. So we're going to have the force of gravity on the player by the earth, and then we're going to have a force, equal force of normal on the player by the ice, and then we have a force of friction. Actually, since it's friction-free, frictionless, there's no friction, and a constant velocity, we are done. So we got nothing there, so we'll have the force of normal minus the force of gravity. So it's exactly like the bird on our perch. That's because they both have 0 accelerations. All right, so for the ball player, again, we're going to just do up as positive, right as positive. Why not? If you have something different, it's not the end of the world. So the downward is the force of gravity on the player by the earth, and the upward force, I need to be getting really sloppy here. So this upward force of normal on the player by the ground, and then because we are sliding, our friction is to the right. So this is the force of friction on the player by the ground. And so in the x dimension, we have the force of friction, and that's it. That's the positive direction. That's because the acceleration is actually going this direction. We don't need a force to go to the left. We just need inertia. Inertia doesn't take anything at all. And then in the y, again, we have the normal force positive minus the force of gravity. Okay, so again, inertia carries them forward. This direction here better be the same direction as the net force. So since we said this is positive direction, this is a positive acceleration, so we better have a positive net force. In other words, there's no indication of which way they're moving. All right, for the chandelier. So I'm just going to draw a line like that. Up, again, is positive. So we're going to have a downward force of gravity on the chandelier by the earth. And then we're going to have an upward force of tension on the chandelier by the chain, the chain. So I'm going to use H for chain. Why not? Chain, chandelier, and the x dimension, nothing. And we get the force of tension minus the force of gravity. And those two are going to be equal in magnitude because, again, we have no acceleration. So those two are exactly equal. All right, so for this guy, we have a bucket that's being raised into the well. Up is positive, so we're going to have a force upward. So the force upward is going to be the force of tension on the bucket by the, let's call it a rope. And then, of course, we're going to have force of gravity going down, the force of gravity on the bucket by the earth. And because how it's moving, it says constant velocity, it tells me 0 acceleration. These two need to be equal. So again, nothing in the x here. We'll have the force of tension being the positive force minus the force of gravity being the downward force. And those two are going to be equal. And this is actually going to sum to 0 because the acceleration is equal to 0. Please, please, please remember that. It's like the first rule in physics. Remember, forces cause accelerations. They cause a change in velocity, okay? All right, for the skydiver, here's your system right here. It says he's just left the plane, accelerating downward towards the ground. So we're going to have a force going down, force of gravity on the skydiver from the Earth. Nothing on the X there, so we're just going to have the force, negative force of gravity. And there's initially no air resistance, but the air resistance is interesting. It's going to get higher and higher. It's going to raise up. So the force of friction on the skydiver by the air is going to grow. That's because as he goes faster and faster and faster, more and more wind is hitting his body, and is causing him to to change his acceleration. So this is what it would look like as you jumped out of the airplane. If we had a VT graph, what would happen here is you would start with a pretty high slope here. That'd be 9.8. And then as he went faster and faster and faster, he would reach what we call terminal velocity, and then we have no slope here. So here the acceleration would equal 0. And then if he decides to throw the chute, it would pull up like this and be now to another new constant velocity. This is the acceleration of 0 as well. And these 2 points are what we call the terminal velocities. Okay, so from here, these are called terminal velocities. And what that means is there's no more acceleration. And when that happens, we're going to have our force diagram is going to have the force of gravity be exactly equal to the force of friction on the skydiver by the air resistance. Those two forces have to be equal. Those two forces have to be equal in this phase and in this phase. And it's kind of interesting to note that this is a fast speed and this is a slow speed. So this is fast, and this here is slow, but the force diagram doesn't care how fast they go. Don't forget. So this is slow, and then we have a faster. We have 2 different terminal speeds, depending upon if it has this parachute open or not. So this is the point where the parachute opens. It's the parachute opens. And what will happen is because we have a larger surface area fronting the wind, it's going to cause a great amount of drag, creating an upward acceleration. That means this thing is going to be really big when he opens the parachute. That force of friction is going to skyrocket, giving you a positive acceleration indicated by this little slope right here. This will be a positive slope right there, and that's going to be a positive acceleration. And then as he slows down, the friction will come back down and then be matching. It'll then match the force of gravity, and then we're back to the slower terminal velocity where he hits the ground at a much slower speed. And that allows him to survive this whole ordeal. Okay? There's a lot going on there. So please, please, please watch this again if you need to and ask questions in class. Okay? All right, for the skydiver, I think I already went over this a little bit. For the skydiver who's descending at a constant speed, constant velocity, this is terminal speed. There's my system. You could do it one of 2 ways. You can do the system where you have your system is all that, or you could have a system of just the skydiver. So I'm going to use a system of everything. So we'll have a force of gravity on the skydiver by the Earth, and then because it's constant velocity, I'll have the force of friction on the skydiver by the air. Actually, it's on the parachute, but let's just call it the system. Okay, the whole thing is a system, and then so this will be equal to this. So nothing there. We'll have the force of friction minus the force of gravity, something like that. And those two would be equal. However, if you decide to do the system of just this guy, you just replace this with tension, replace this with tension, and it's the same thing. Okay, so it doesn't really matter what you call it. If your system changes, you got to look what's external. It's not the end of the world. If you did it one way or the other, it's okay. Basketball in the highest point. So your system is going to be this guy right there. That's just going to be the force of gravity. Force of gravity on the basketball by the Earth. So we have a minus force of gravity happening in the y dimension. That's it. There might be a little bit of air resistance, but I wouldn't mention it. All right, for the hurdler. So the hurdler is just going over the top. There's no contact. So yeah, there's just force of gravity. Yeah, there might be a little bit of air resistance. Can't avoid that, but really you have to be going kind of fast in order to experience. Have a large surface area, like a piece of paper falling. You know, it's gonna have a lot of air resistance compared to its weight. But I would say there's a little bit, but let's just make things simple. let's just make it minus force of gravity for this one. That'd be fine. So we just have that. And that would be on the hurtler by the Earth. Good, done. All right. The airplane. Because the airplane, how is it moving? Most important is constant velocity level flight. All right, so we go over here. We're going to have forces going down and up, left and right. They're all going to equal, they're going to add up to equal to 0. So this has to equal this, and this has to equal that in order for it to be balanced. This is the force of gravity on the plane by the Earth. This is the force of lift on the plane by the air. This is the force of drag, or friction, if you will, on the plane by the air. That's the air resistance. And over here, this is the force of a push or thrust. Thrust by the engine. You know, you got the whole interaction thing where it's pushing this way, pushing that way. So that's going to be the force of thrust, or it's okay if you don't have thrust. It's not the end of the world. I don't really care what they're called. Just put a force to the left that's going to push the plane forward. Whatever you call it, you go nuts. But the force of thrust is going to be provided on the plane by the engines themselves. So engine, I'll use an N for engine. Why not? So in the x dimension, again, we're going to say this is positive, and we'll say that's positive. So up, we're going to have, in the x dimension, we'll have, in the positive, we'll have the force of the friction minus the force of the thrust. This one I might make an argument to switch this around, but you know what? I'm going with it. Don't care. So in the y dimension, we have the force of the lifting force, or the push force upward by the air, whatever you want to call it. Doesn't matter to me. And then the force of gravity going down. And this is all going to sum to 0 when you add them all up, because it's a constant velocity level flight. And so if you go by a manual, or you just go to a flight school, the very first page of your flight manual will have this picture shown very clearly in the very first chapter. And basically what happens is, you want to climb, you want to get higher, the lifting force has to be bigger than friction. Okay? I'm sorry. The lifting force has to be greater than gravity in order for you to go upward. If you want to go faster, the thrust has to be greater than the air resistance. If you go slower, the friction is going to be greater than the thrust. So it's just the interplay of these forces here. And if you want to go level, just make sure left and right is balanced, up and up down is balanced. That produces level flight. The skier is exactly like the airplane, except you got different forces here. So you got the force of the tension, you got the force of gravity, you got the force of friction, and then you got the force of the normal, or whatever you call it. What the heck, we'll call it normal force, because we're going to go through the ski. Why not? We'll go right through where the feet touch the ski. And so these forces will all balance out in the x dimension, and then we'll say this is positive, and this is making more sense to make the right positive, because that's the way it's actually going. So we'll have the force of the tension minus the force of friction, and then in the y dimension we'll have the force of normal going upward minus the force of gravity. And there we go. And if it's constant speed, constant velocity, that means that this is equal to this, and that is equal to that. So we know that they both are going to sum to 0, both of them. And if you want to go accelerate faster and go faster and faster, that means your tension has to be greater than your frictional force. All right, and if you would like to rise up out of the water, the normal force has to be bigger than gravity to get you to accelerate upward, but then once you're up, you want those two to be balanced. All right, for the person leaning against the wall, this one is a little trickier. So we're going to have our person here, and we're going to have 4 forces, one straight down. That, of course, we know is the force of gravity on the person by the earth. We know that. And then we have this one will be the force of normal on the person by the floor. And then we know, this is where everyone kind of messes up. I always see students mess up. They're going to see this person pushing against the wall like that, but that's not on the person, that's on the wall. So we're going to get a force this direction, the force on the person of normal. Let me go back, I messed up. It's the force of normal on the person by the wall. See? So we're not talking about the force on the wall, we're talking about the force on the person. Students always get that wrong. And then there's got to be a force going this way. And the question is, where's it coming from? Well, it's got to come from the feet. So that's the force of friction on the person from the floor. Isn't that weird? See, the person wants to slide backwards, but the tennis shoes are preventing that from happening. Let's just think about it for a second. Let's say you put roller skates on. Well, you're just going to slide right away, out the other end. So, you've got to have some friction pulling you back. And again, we'll do positive. We know that drill. So in the x dimension, force of friction is in the positive direction from the floor, and then minus the force of normal. Again, since we are leaning against the wall, we're all going to sum to 0. And then if I want to do the x dimensions, the x, I have the force of normal minus the force of gravity. Okay, there we go. Pretty straightforward. Sum to 0. Can't spell 0. I'm running out of time here. Okay, so here we have a person with a sled. So I'm going to have a force of gravity. We're going to have the tension going this way, the force of tension. We'll have a little bit of normal going that direction, and we'll have some friction going this way. And it says the sled is at an angle. So what we have to do here is we're going to dissect this into two components. We have the x component of that tension, and then we have the y component of that tension. These red and green arrows are not really part of your free body diagram or your force diagram, so you kind of have to be careful. In the x dimension, we're going to have pencil turned off. We're going to have the force of tension in the x dimension, then minus the force of friction. And in the y dimension, we've got three things. We got the force of normal, plus the force of the force of tension in the y dimension, because they both go up, and I subtract the force of gravity. Now, we also know that the force of tension in the x is equal to F cos theta. And that's the theta sitting right in here, and then the force of tension in the y, of course, is F sine theta. We'll talk more about that later. If you missed that lesson, we will do something with that at a later time. Okay, so here we have our ring. It says for the ring itself, so here's my system right there. It holds 3 ropes together. So I'm going to call this rope 1, rope 2, and rope 3. So I'm going to say this is the force of tension 3, and then over here I'm going to do T2, and then over here I'm going to do T1. And you can see that each one of these, except for T3, has components. So you get a component this way and a component that way. Those are going to be equal and opposite, and then we'll have the component up and the component up. So I'll have the tension 1 in the y, tension 2 in the y, and tension 1 in the x, tension 2 in the x. So this will be fun. So in the x dimension, we have T2 in the x dimension, and then we subtract T1 in the x dimension. And you can use sines and cosines with theta if you like. And then in the y dimension, we're going to have T1 in the y dimension plus T2 in the y dimension, and then minus T3. And there might be a little bit, it looks like pretty small there. Compared to this big old mass, I'm thinking this ring right here isn't really a whole lot of mass, so I'm not going to I might have a little teeny tiny little guy, but I realize T3 is going to be a whole lot bigger because of that big old mass there, and that ring is like minuscule, so we can just kind of ignore that gravity. Why make things more difficult than it really needs to be? Yeah, I think you can agree. It sounds like it's already difficult, doesn't it? Let's just not make things harder than we need to. All right, let's go on to the next one. This one's actually kind of interesting because here's your gal, and we know we have gravity going straight down. I'm going to drop all the triple subscripts. If you have a question about how to do that, let me know, but you guys need to figure that out. I'm not going to do it anymore. You need to do that until I tell you we're done, but I'm done with it. So then there's a force of tension going this way, or actually it would be tension going this way, and then you can see that there's going to be a component going that direction, and then there'll be a component going that direction. So we got tension in the x, tension in the y, and so in the x dimension we'll have tension in the x. That's about it. And then in the y, in the y we'll have tension in the y, which is positive, and then we subtract the force of gravity. So this will have an unbalanced force we'll have an unbalanced force, In other words, it's going to accelerate, and it's going to accelerate this direction. So she might be swinging out to the highest point. Even when her velocity is equal to 0, her acceleration is still pointing back to where she came from in the middle of the swing. Ain't that interesting? We'll talk more about that later. We have a whole lesson right on what's going on with this gal enjoying this swing. We have a whole lot of physics to cover before we get to that idea. But man, it's going to be fun when we get there. Because we're going to be swinging on swings, you know? It's going to be great fun. All right, let's get the squirrel. I think I did this for you in class already. So we did the dot here. We'll have the force of gravity. We'll do friction going this away, and we'll do normal going this away. And it depends on what class you're in. I did it a little bit differently. If you're in the regular class, you may have gotten just the x and y components of normal and friction. If you're in the AP class, you may have rotated the axis and lined it up with the ramp, and you would have you would either dissect normal and friction, or you would dissect the force of gravity. So I'm going to leave it at that, but just make sure you have all these forces present. And then we get to the skier. I'm going to say, because this is a skier, I'm going to say that there is no friction. I'm just going to make that leap. If you have friction, it ain't the end of the world. It's no big deal. But I'm just going to say there's no friction. So there's a force of gravity going straight down, and then there's a normal force going something like that. Yep, and so there'd be like a net force. When I add these up, there'd be like a little net force going like that direction, which is down the ramp, which means he's going to accelerate down the ramp, because it's more fun to accelerate down the ramp than it is to hang out or go at a constant speed. So if we had no friction, we would just accelerate down the ramp. Now, we're not going to include that in our force diagram. That's not really part of it, but just so you know, if I were to add these up, I would get a force. This is my net force diagram, our net force vector. Again, pointing down the ramp, my net force, because I want it to be fun. You know, I want to accelerate. If you didn't accelerate and included friction, that's cool too. All right, so this is what okay, so in my class last year, they had, and you'll see it if you look in the backboard, but anyway, so there's my students last year, was kind of fun because they drew like this giraffe, kind of a picture, okay? So don't make fun of my giraffe. Oh, this is terrible. Oh, this is terrible. But here's the giraffe, okay? And he's in outer space. So here's the Earth, yeah. And he's just kind of floating around. In fact, oh shoot, I lost my picture. Oh no, that's no good. So I get to redraw. So he had a name and everything. He was like a little mascot. So I'll just kind of make him like this. So here's the giraffe. And the giraffe is floating out in space. And basically, here's his force diagram. Ain't that neat? Because the Earth is just so far away that he doesn't feel any force from the Earth. And so there's nada, it's the null. And what he'll do, if he's going with a certain velocity, he'll just maintain that velocity as he goes, which means the acceleration equals 0. See, it doesn't take anything to keep moving. Yeah, it's got inertia. Kind of interesting. That's the easiest example I can come up with. Boom, how easy is that? It's a dot. But you got to go away from the Earth. This little thing over here, that's the Earth. That's so far away. No influence. We're like deep outer space. And this is his space suit. It's a little bubble there so we can stay alive. Anyway, Bentley was his name, old Bentley. So anyway, he's like our class mascot, so to speak. Anyway, hope you enjoyed this. Have a good rest of the day and a good weekend. Goodbye.